Hello, ladies and gentlemen, and let's go ahead and let's talk about what we were going to talk about today in class. We are going to look at different models. We'll look at our exponential growth and decay models, Newton's laws, and our logistic growth and decay model. The first one we'll look at is our law of uninhibited growth. So uninhibited, what does that mean? Uninhibited, it is not contained by anything. There aren't any factors outside that would limit or try to contain the amount or the growth that is happening. So we could look at population, the growth of cells, any of those things, and if we live in an imaginary world where there are not any outside factors increasing in, like the limit of space, our function or our objects that are growing could grow infinitely and boundlessly, or decay. Our growth and decay model is going to be A is equal to A sub 0. A sub 0 is our initial amount, times E raised to the K T, where K is our rate. If K is positive, we will have growth. If K is negative, we will have decay. We are using E here because our population is growing, and it is not growing at specific different times. It is continually growing. It is continuous growth, so we are using E. Let's look at our first example, and I accidentally already did this, but let's look as I was practicing. Yes, I know, Miss France was practicing for this video. We can just ignore all of this a minute. All right, so first up we have growth of an insect population. The size P of a certain insect population at a time T follows the function P of T is equal to 500 times E raised to the 0.02 T. Our first question wants us to determine the number of insects at T equals 0. So we can simply substitute in our T of 0. And as you all should know from Math 1 and beyond, that is going to be our initial value. And our initial value is our 500. So we start with 500 insects. All right, next up we are asked to determine the growth rate. Our growth rate is our K value. So in this case, our K value is 0.02. Typically, how do we talk about rates? We talk about them in percentages. So our growth rate is going to be, our growth rate, if we change it into a percent, we're going to multiply by 100, which is going to be 2%. So the population of the insects is growing at 2%. Next up, what is the insect population after 10 days? That's another simple substitution. So we need to find the population at 10 days. So we will have 500 times E raised to the 0.02 times 10. And if we enter that into our graphing calculator or whatever calculator at hand, we get that our population is 610.7. Now, can we have 610.7 insects? I don't know about you, but I come from a world where you either have an insect or you don't. They're not given it in tenths. So in reality, at 10 days, we really only have 610 insects. All right, next up, we are finding when the population reaches 800. You have two options here. One option would be to graph our function and then graph a second function of a horizontal line 800 and see where they intersect. That would be kicking it old school Math 1, solving our exponentials. Or we can now use our logarithms. And in this case, we're going to use our logarithms, and we have an E, so we will use the inverse of E, which is the natural log, and our calculation will work out quite nicely. So, reach 800, so let's let 800 is going to equal 500 times E raised to the 0.02 times T, because now T is our unknown. So first thing we need to do is we need to isolate, so we must divide by 500. And we get 8/5 is equal to e raised to the 0.02t. Now our issue here is still that our unknown is inside the exponent. So somehow we need to bring it down to earth. We need to undo the e, the raising. So let's take the natural log of both sides. All right, now using our properties of exponents and logarithms, we have a power inside a natural log, so we can go ahead and write that in front as multiplication. And I'm going to come right up here. So I will have the natural log of 8/5 is equal to 0.02t times the natural log of e. Wait a minute, by golly, what is the natural log of e? The natural log of e is just 1. This is why we would like to use the natural log instead of the regular logarithm. Now all we need to do is divide by 0.02. And we get that our t is equal to the natural log of 8/5 divided by 0.02, which when we enter that into our calculator, it is 23.5 days. So our population will reach 800 at 23.5 days. I sure do not want to be around for that. Last but certainly not least, we need to figure out how long it will take for the insect population to double. Now, if we are doubling, it doesn't really matter how much you start with or how much you start with. We're always going to have a ratio of 2. But let's look here. We have 500, so really we want to know when will it reach 1,000. So I will, of course, divide by 500. And look what happens right here. You get 2 is equal to e raised to the 0.02t. This is because, as I was just saying, it doesn't matter how many you start with in the population. If you're looking at doubling, you're always going to have a 2 here. It's very similar to our half-life problems that we've done in the past, where you want to know how long it takes for it to get half of what it started with. It doesn't matter what you start with, you're looking at half. All right, so now our unknown is in the exponent, so we take the natural log again of both sides. We can use our properties of exponents to write our power in front. Oh, there we go again. Natural log of e is just 1. So really all we need to do is divide by 0.02 on both sides. And we get that our time is equal to the natural log of 2 divided by 0.02, which is 34.657 days. So it'll double in 34.657 days. All right, next up, let's look at some decay. The most common decay that you're going to see is radioactive decay. All of you who have taken chemistry have done plenty of these problems. So let's see. We're looking at strontium-90 is a radioactive material that decays according to the function A of T and is equal to A sub 0 times e raised to the negative 0.0244t. Negative means decay, where a sub 0 is our initial amount present and a is the amount present after a time t in years. Assume that scientist has a sample of 500 grams of strontium-90. What is the decay rate of strontium-90? Our decay rate of strontium-90 is our K value. Our K value is negative 0.0244. As we said before, we typically look at that as a percentage, so we would multiply by 100. And that is a decay rate of 2.44%. Next up, they want to see how much is left after 10 years. That's our simple substitution again. So A of 10 is going to equal 500 times E raised to the 0.0244 times 10. We will put that into our calculator and we get 391.7 grams. Next up, when will there be 400 grams left? So we'll have 400 is equal to 500 times E raised to the negative 0.0244 times 10. We will isolate and divide by 500. And we get 0.8 is equal to E raised to the negative 0.0244 T. Oops, and it looks like I put another 10 here just out of the first one. So let me fix that so you guys aren't going back and going crazy. Now we need to get our exponent in front, so we need to take the natural log of both sides. Taking the natural log of both sides will allow us to write our power in front. So we have negative 0.0244 T times the natural log of E. Our natural log of E is just 1. So all we need to simply do at the end is divide by negative 0.0244. And put that into our calculator, and we get that T is equal to 9.145 years approximately. So in 9.145 years, we will be left with 400 grams of strontium-90. Next up, when is the half-life? Our half-life is the amount of time it takes to get to 1/2 of the original amount. I'm going to squeeze this one in here because it looks like I didn't leave a blank slide next to it. So we need to look at how much it takes to get to 1/2. 1/2 is going to be 250 is equal to 500 times E raised to the negative 0.0244 T, and we are solving for T. Very similar process. We'll need to divide the 500 over, take the natural log of both sides, which allows us to write our power, where our unknown is, in front of the natural logarithm, and solve for T. Doing so, we get that T is approximately 28.4 years. So the half-life is 28.4 years. Next up, we're going to look at Newton's law of cooling. Those of us who have taken chemistry should be familiar with Newton's law of cooling. My homeboy, Isaac Newton, came up with this law. It looks at the temperature of a heated object at a given time can be modeled by the following function. So we have the temperature at a time is equal to the environment's temperature, so it might be the room temperature or whatever the object is in, that constant temperature, plus we have the initial temperature of the heated object. So if it's, say, something coming out of the oven, our temperature of the room would be T, then we have that initial heated temperature, so however hot it was when it came out of the oven, minus that room temperature again, if it's the case that sometimes you call it the ambient temperature, times E raised to K, which K is our rate at which it is dropping. And it's going to be dropping, the temperature, it will cool off, so it is going to be negative times the time. So let's look at an example. We have, ooh, yummy yum, pizza time, cooling time of a pizza pan. A pizza pan was removed at 5 p.m. from an oven whose temperature is fixed at 450 degrees Fahrenheit into a room that is a constant 70 degrees Fahrenheit. After 5 minutes, the pan is 300 degrees Fahrenheit. At what time is the temperature of the pan 135 degrees Fahrenheit? Alrighty then, let's look at this. So let's first define some of our variables, okay? So we are looking at the pan as it comes out of the oven. As the pan comes out of the oven, it is leaving the oven, which is 450. So that is actually our U sub 0 is 450 degrees. Then we know that the room temperature is 70 degrees, so that is our T. And what else do we know? What else do we know? What else do we need to know in our equation? In our equation, we know that they also tell us that after 5 minutes how hot the pan is. So our U of 5 is equal to 300. Now let's look at A. They want to find out how long it takes for the temperature to be 135 degrees. Before we can answer that question, actually, we really need to figure out what our K value is. So we can figure out what our K value is. So let's do that. We know, and we're going to use this U of 5 as 300. So I know my temperature of the pan is 300 degrees. It is 300 degrees. We know our room temperature is 70. We are going to add to that our starting temperature of the pan, subtract the room temperature, and times that by E raised to the K. We do not know what K is, but we do know our time, and in this case, our time is 5. So now we will need to simplify and solve for K. So when we simplify and isolate, we're going to get, we're going to get 230 divided by 380 is equal to E to the 5K. Now I know I didn't show some steps there, but I subtracted 450 from 70, added it to 70. Excuse me. I subtracted 450 from 70. I subtracted my 70 over from the 300, so 300 minus 70. Then I divided by the 450 minus the 70. And I got 230 over 380. And now I need to solve for my K. So what I need to do here is I need to take the natural log of both sides, which allows me to write my exponent in front. Oh, look at that again. Natural log of E is equal to 1. So now all I need to do is divide by K. When I divide by K, divide by 5 to find K. When I do that, I get that my K value is negative 0.100418. Now I can use this to figure out at what time the temperature is 135 degrees. So now, to finally answer A, I do 135 is equal to my 70 plus 450 minus 70 times E raised to the negative 0.0, we want 1, 0.00418 T, and now I need to solve for T. So in doing that, I am going to get and I put that in the calculator and isolate the E. I'm going to get 65 over 380 is equal to E raised to the negative 0.1000418 T, which then I can take the natural log of both sides and write my exponent in front, and I will get, when I solve for T, I get T is equal to 17.58 minutes, which is 17.58 minutes after 5 p.m. is at 5:18 p.m. Next up, I need to find the time that needs to elapse before the pan is 160 degrees. Very, very similar process here. You're going to let it equal 160 degrees. We know, substitute our other values in, so we have 70 plus 450 minus 70 times e raised to the negative 0.10041 t, and you're going to solve for t. When you solve for t, you get that it is at approximately 14.343 minutes. And our last question that they ask us is, what do you notice about the temperature as the time passes? Well, as the time passes, it approaches 70 degrees Fahrenheit. It approaches the room temperature. And graphically, we see this because there is a horizontal asymptote at 70. Temp approaches the room, the room temperature, which is 70 degrees Fahrenheit. There is an HA at Y equals 70. Good deal. Last but certainly not least of the models that we need to talk about is the logistic model. Okay, this one might be a little new for some of us. So our logistic model, we have in a logistic growth model, the population P after a time T obeys the equation. The population P of T is equal to C, where C is a carrying capacity, divided by 1 plus A times E raised to the negative BT. So the carrying capacity is the amount that a certain, say if we're talking about population that maybe a city can hold, or if we're talking about cells dividing that the body can hold. The model is growth if our B value is positive, and it is decay if our B value is negative. So just like before, and we are using E here as well because it is also going to be continuously growing or decaying. So when we look at this, it is a little different than exponential because it will eventually reach our capacity. So it reaches the capacity and it levels off. We have an inflection point both when we are looking at both of the curves, whether it be growth or decay. This is halfway between the starting and our capacity, and it is where the curve kind of flips. It's where it's concave up or opening up here, and then down here it's opening down, so we call that concave down. On the decay model, it is concave down first because it's opening downward, and then it turns at the inflection point and it becomes concave up. So there's some good calculus words there. Some properties. The domain is the set of all real numbers. The range is from 0 to our carrying capacity. There are no x-intercepts. The y-intercept is our initial population. There are 2 horizontal asymptotes at 0 and then 1 at our carrying capacity. It's where it approaches and doesn't reach, or could reach, because we know horizontal asymptotes it could reach. And then our population is an increasing function for p is greater than 0 and decreasing for p is less than 0. And then we have our lovely inflection point, which is half of the carrying capacity. The graph is smooth and continuous with no corners or gaps. All right, let's look at an example. Birthdays. We have the logistic model, P of n, which is equal to 113.3198. divided by 1 plus 0.115 e times e raised to the 0.0912n models the probability that in a room of n people, no two people share the same birthday. First of all, it wants us to graph this model. So we will graph this model and make sure when you divide that you are using your parentheses for the denominator. So in a room of 15 people, n equals 15, what is the probability that no two people share the same birthday? So that is going to be our P of 15. You could either look at this on the table or you could substitute it into our equation. Oops, 0.0912 times 15. In doing that, we get 78.062. So the probability that no two share the same birthday is 78.06%. Next up, how many people must be in the room before the probability that no two people share the same birthday falls below 10? It must fall below 10. So let us go to the next page since we have more room. And falls below 10. So we need to know 10 is equal to 113.3198. Oops, let me make that clearer for us. 0.3198 divided by 1 plus 0.115 e raised to the 0.0912 x. All right, so we need to do some algebra here. So So we will multiply by our denominator, and we will have 10 times 1 plus 0.115 e raised to the 0.0912x is equal to 113.3198. I'm going to divide by 10 over, and I will just be left with 1 plus 0.115 e raised to the 0.0912x is equal to 11.33198. Then I need to subtract 1 over and divide by 0.115. Excuse me. So then I'll have on the left, I'll have e raised to the 0.0912x is equal to it becomes 10 because I subtracted 1.33198 divided by 0.115. And then I need to take the natural log of both sides, which will allow me to write my exponent in front of the natural log, and then divide by 0.092. When I solve for x, I get x is equal to the natural log of 10.33198 divided by 0.115. That entire quantity divided by 0.0912. And we get x is approximately 49.3209. So our question remains. It asked us, how many people must be in a room before the probability that no two people share the same birthday falls below 10%? It would be about 50 people. About 50 people. And our last question, what happens to the probability as n increases? Explain what this result means. The probability decreases, but at a much slower rate. It is decreasing at a much slower rate. And that is because if we look at our logistic curve, it slows down as it approaches our horizontal asymptote. I will talk just very briefly about building exponential, logarithmic, and logistic models, because really all this section contains is you inputting data points into your calculator using STAT, then using the regression function on your graphing calculator to look at the exponential, logarithmic, and logistic models for that data set. As we know, we should see if we have a data set that is trending upwards, it's exponential growth, trending down, exponential decay. We could have logarithmic as well. So those are two possibilities, which we have those on our graphing calculator. And then our logistic growth, if it looks as though it is trending up and then hitting a point where it is slowing down. So I will let you run through these examples on your own. The gist of them are, though, you need to input those values into your STAT, edit STAT, then you need to go to Stat Calc and click the corresponding regression model that fits that data as well. So I will answer questions on these tomorrow. Good luck, and hopefully that you found this video helpful and you were able to do your homework. I will see you all tomorrow.